Temporary earthworks retaining solutions. Temporary earth retaining structures are required to retain earth in the temporary term. There'll be endless reasons why you'll need to do this on your site. However, which type of wall you use can really help you along. I won't be focusing on permanent works in the temporary term, such as a contig piled wall, propped various levels, or secant piled wall. But what I will focus on are the types of wall that I often see used on site as part of temporary works. So if we have a look at some of the typical examples, I've got some here. So the first group is gravity walls, which means that they rely on their mass for stability. The first example of this type is a mass concrete gravity wall shown. Ignoring what I just said about permanent works, but the large mass concrete gravity walls like this are not often used as temporary solutions, as it requires a significant amount of material and concrete, and not very efficient or sustainable. But it might be already on site, so you might be using it if you're justifying an existing structure for additional loadings from, say, a mobile crane operating behind it, in which case it would be necessary to get an engineer to assess the wall to make sure it remains stable. A small version of a gravity wall such as this would be when Kelly blocks or concrete blocks are used at the edges of pile mats to provide that edge detail. If you've got a high level pile mat, that's mass concrete gravity walls. The next example is a gabion basket wall. This is a series of containers, rectangular or cuboid in shape, with material, and they're filled with material and then stacked to create a wall that generally leans back from the open face. You can see a design here that we've done, and the structure is usually towed in at the base and has some form of prepared subbase to take the increased bearing pressures beneath the wall. An alternative to this solution is to use bulk bags or ton bags filled with soil. This option costs a lot less and also looks doesn't look great, but it's temporary. It's winning no beauty contest, but it's doing a job and serving a purpose, so that's fine. On this gabion basket wall, I incorporated some posts, key clamp posts, as edge protection, and then the face of the baskets can also be seeded or planted, which can produce quite a nice finish for landscaping purposes if it's going to be used for a longer period of time than just temporary. A similar method to gabion basket is the gato block wall. These are like huge concrete walls, huge concrete blocks, which are piled together and then put together a bit like Lego blocks. They're precast, but you require some larger plants to move them around on site. They're essentially just like similar to Lego block work, which I'm sure you all have hidden away at home. The next one is the cantilever L walls. So these operate similar to a gravity wall, but use the weight of fill to stabilize the toe. They're often used on transfer sites or material transfer sites, and they can be flipped around. You don't have to put the soil on the toe, but it really does help you. If you turn it the other way around, then you're not exploiting its abilities to provide an additional stabilizing force. The next type or group of wall is embedded walls. This covers trenching systems that you can see here with proprietary trench boxes or manhole boxes. This group also covers simple trench systems with boards and wailers or sheets. That's if the excavation needs to be a bit more bespoke. For example, if the excavation, if there's a lot of services in the excavation that you need to chop and change around or run through, then it's usually beneficial to have sheets because you can adapt them to suit. And then this type of wall, the embedded walls, also covers the sheet piled walls as well, which these can be propped, tied, or they can be pure cantilevers. They can be quite small sheets installed via an excavator, or they can be much larger, being installed with a specific sheet pile rig, but both trenching systems and sheet piling are very common. King post walls are constructed from posts in the ground that have large either concrete panels or timber panels, which is called lagging, to retain the fill. These systems are great in the proper application. you can see a photo here of the post being installed in the ground, and then the concrete panels being installed between the posts. The posts below that level, that ground level there, is just posts, which can be either driven straight into the ground or encased in a pile like a plunge column, and then the panels are inserted to retain the soil to fill behind. And then finally, we're on to the odds and ends, which don't really fit in either of these categories. The first being combined systems. So it's sometimes required that multiple systems are used together, which is often the case in my experience. A recent example of this is when we've used a legato blocks as a hard face, and then with the geogrid tails running back out of that. So we've got hard face and then but very steep. So using the combined systems to work together, it works quite well when you've got, depending on the constraints of your job. Anchored earth solutions are really good. So soil nails or ground anchors, such as platypus anchors, are installed, which then utilize the resistance of the soil to provide support. They must be long enough to rely on the soil strength, which is outside the zone of failure, being the fact that if you need to extend into that stable zone, otherwise it's similar of sitting on a tree and cutting the branch that you're sat on. It's not a good idea. And then finally, we've got the mechanically stabilized earth structure, also known as geogrid reinforced walls or slopes. This is a slope reinforced with geogrid at regular levels to increase the stability of the soil in that structure. They are built in layers with geogrid tails reaching back and then tying the soil block all together. These structures can have some high loadings and provide a solution covering quite a vast area. They're also great for some minor details, such as retaining the ends of raised working platforms and small batters as a alternative to the Kelly block solution I mentioned earlier. The example shown in this picture is in Royal Wharf in London on the Thames. And here we utilised the reinforced earth structure to enable the project to be completed in 2 phases. The new area was about 3 meters higher than the existing level, so we created a steep embankment just right along that phase line. The walls need to be constructed against some kind of former, and in this case we used a scaffold hard form that you're able to construct your face against. An alternative would be to use some bent up mesh rebar in a kind of a triangular shape. So as you make each layer, then you put the next layer on and you keep going. Or alternatively, you can use a movable shutter. But essentially, it's important that you need to have some form of hard face to construct up against. And then the faces of the wall, they can be used to suit the different applications. So most of the time, it's left as just a geogrid face in the temporary term. But if it's going to be left for longer, then it can be seeded or covered with a harder face. The reason why it's usually covered is to protect the geogrid from damage from UV rays, and also to prevent scouring away the face soil that's in the face there. So that really covers the big ones in temporary earth retaining structures in a nutshell, really. Before we move on to some case studies on some of these structures, I'd just like to mention some areas to keep in mind when thinking about retained earth structures. The key one is failure and how to avoid it, and I'll just go into different modes of failure. So we've got some illustrated here. The structure itself, so the top left, we've got the structure itself overturning under the forces of the applied loads, uplift from buoyancy effects or heave at the base from hydrostatic water pressure, global failures such as sliding, slip failure and bearing failure, and then also local failure of a particular element of the structure, because you're only ever as strong as your weakest link. The difference between local and global stability in terms of the soil failure should also be taken into account. It's not always the larger slip circle that causes the issue. It could be a smaller one. So all the credible failure mechanisms need to be reviewed and checked. Another couple of tips to be aware of: loose fill behind the walls. Sometimes walls are constructed in a cutting and then backfilled with loose soil or loose fill. So the soil loading behind the wall may well be much greater than you expected if your borehole was taken like 5 meters away from the back, it might not be as good as you hoped. Good site investigation on soils that will be retained, and also the soils that will be loaded as part of your wall is key to driving an efficient solution. And what springs to mind is the GIGO term, which is garbage in and garbage out. If the information available on the wall or the soil is of poor quality, then the output of the design is going to be more than likely oversized, inefficient, and more often than not on the conservative side, because the conservative assumptions would have to be made. But on the flip side, it could also be that the site investigation is so lacking that crucial details are missing altogether, which could lead to failure. So this could be perhaps a large underground service chamber, or layers of running sands behind, which could cause serious issues. These are the unknown unknowns, which we try and bottom out as much as we can, really know as much as we can, because good information drives good design. Another point to note on retaining walls is that any high point loads that may be applied behind the wall from building foundations or crane loadings really need to be taken into account. Walls are generally designed for blanket surcharge, but high point loadings need to be reviewed separately, as they may well present a worse case. It's worth considering if the crane can directly load the top of the wall, as this can act as a stabilizing force. That's kind of counterintuitive by bringing the crane or the load closer to the wall or on top of the wall to reduce the risk, but it's true, and it's something that we've employed on a number of occasions, just like this example here, where we avoided loading services in a footpath and also stabilized the retaining wall all in one swoop. The principle is the same of the kind of the children's building blocks. If you build a set of blocks and apply a force from the top, then the tower becomes more difficult to push over. It becomes more stable. And I love these basic engineering fundamentals. That they're very simple, but they are effective, and they do work. Another one is groundwater control, and the account of water pressure is really crucial, as water pressures can be very high because water has no shear strength. It cannot hold itself. This can be easily solved by drilling regular holes at the base of the wall to drain it, but this simple measure cannot always be deployed. Perched water can cause issues as well, and they can also show up on boreholes, suggesting false groundwater levels. So I'll just cover perched water quickly. It can be spotted in the borehole log if it's deep enough, because the water table will show up at multiple levels. There'll be multiple levels of water strikes independent of one another. And the way that they work is that there's an impermeable layer or lens, such as a clay layer, in the made ground, preventing the water from draining away and hence being perched above that true groundwater. The creation of retaining structure in an area of high groundwater is normally associated with a change in groundwater conditions. So, for example, if you've got a basement and the excavation needs to be kept reasonably dry during construction, this is often done by pumping from sumps in the excavation. But this has an effect on lowering the groundwater table inside the excavation, thus promoting flow through. So it's important to keep that in mind, because that flow through can lead to localized instability of the soil, where the hydraulic gradients are the highest. It's something to keep in mind. And if you're going to take one thing away from this slide, it's really that Woody says, don't take groundwater for granted. It can cause some significant issues when you've got deep basements. The water pressures can be very high. Okay, now then, ladies and gents, we're going to get onto some trench boxes, sheet piles and L walls, and we all know that's what you're here for. So let's get down to some business. So trench boxes first. Trench boxes and trenching, it's really common in urban areas, often used to permit utility repairs, installations and replacement of buried services. It's often seen on the roadworks as you're queuing up to those pesky temporary traffic lights. These systems are always temporary, and they're typically used for excavations that are quite narrow but can be up to several meters deep. and they comprise of prefabricated units that are lifted in and out of the trench as necessary, or they can be individual sheets, sheet piles and struts and wailings, as I've mentioned before. So a couple of examples here. They must, by their very nature, be reusable. Because they're temporary structures, their appearance is irrelevant, really. Buildability is essential and made easier with the prefabricated units, such as trench boxes. They're generally safer to use as well, because you can avoid putting somebody in the ground, and it's made, put in the ground, and then it's safe, ready to rock and roll. A couple of examples here. We've got a simple trench box required for an observation pit. We put together, so this was going to be removed. The soil was going to be removed with a back excavator because it was quite a sensitive excavation. The trench box was installed, and then we had either a batter coming down on one side, or an end plate, which is just a plate to stop the soil coming in. It's quite a small excavation. And then the one on the right hand side, that was just to enable the construction of some ground beams, really. So trench boxes with a high strut level, so that the ground beam could be constructed beneath. And then also on section B there, we've got a bagwork wall, which is the bulk bags or ton bags constructed similar to a gabion basket wall, just because the site levels were varied across that. Where sites are congested, it may be required that you use the sheets and wailers instead of a trench box solution, just because of the number of services, and you can pick and choose where your struts go. So that leads us on to sheet piles and sheet pile wailing. This is very flexible. It's a very flexible support system, and often used for both large and small waterfront structures, or in temporary works, as I see quite often. It's often used in poor ground conditions because there's no foundations that are required. The sheet piles are installed, and that is the solution. Although the sheet piles are easily driven from ground level, construction is straightforward even when water is present, because the sheets can be installed from a barge or pontoon, so they're often used on waterfronts. So some notes on the types of wall. They're often able to follow complex plan shapes with ease, really. They cause minimal soil displacement during driving. They can be constructed in conditions of low headroom with a variety of modern installation methods now that cause low environmental impacts, such as noise and vibration. You get the ram where you have the silent piler, where it sits on and uses the piles and then pushes the next pile in. They cause very low vibration and noise, and their speed of installation and extraction leads to a high degree of sustainability because they can be reused. On the negative side, though, they can be expensive if they're used to provide permanent solution, and traditional methods of installation, such as the percussive techniques, can be very noisy and cause a lot of vibration. The wall depth is limited by section size, the loads, and the standard sock lengths. And in certain ground conditions, installation may need to be preceded by water jetting or pre-augering. Typical sheet piles are steel profiled, but timber and concrete types can be used. The typical steel profiles are shown here, and they've got a number of benefits. So there's a variety of cross sections with a wide range of strength, a lack of buckling under heavy driving with stiffer sections, availability in different combinations to increase the wall strength. So you can profile them differently when you clutch them to give you different strength. They're reusable and relatively lightweight, and you can also, there's a possibility to increase the pile length by welding or bolted connections, and where they're clutched together, that can really help with waterproofing for copper dams and such, and also creating that additional geometry to make things a lot stiffer. But sheet piles can also be tied back, so they're not just propped with struts or with cantilevers. So I'll give you a quick example on when we've used this on a project. So in this project, we were tasked with a steep level change directly adjacent to an area that was loaded with some welfare cabins that were based on some square concrete pads. and they're shown on the green squares there. The purple area is an area where we had to construct a capping beam, and that was being constructed at low level. There were 2 levels across this elevation. Section AA, this was 1.4 meters deep, and then because it wasn't that deep, we were able to have a pure cantilever wall. However, in section BB, in the other area, the depth increased to around 2.9 meters. So, and a key design consideration here was the deflection and the ground movement, and this often is the driving criteria for cantilever sheet pile walls. As the depth and the type of the sheet were limited, we opted to tie the sheet back to at 2 levels to provide support to the sheets. No whaler was necessary, as the anchors were installed on every other sheet face, as shown here, and the sequences installation was as follows. So stage 1, the sheets were installed, and then we excavated down to the depth of the first tie to allow that to be installed, and then stage 2 is installing that tie and testing it to make sure that we were getting the correct capacities of the tie. At that stage, once we were happy with the tie capacity, then the following stages would be to reduce down to the next level, install the tie, and then once that final tie level is in, excuse me, then we could finally do the reduced level dig and install the permanent works. The anchors were installed through holes cut in the sheets, and the whaler plates were then used to enable the locking nut to be installed and the tie to be tight to the sheet pile. And this solution worked extremely well. The type of anchors that we used in this job were Vulcan anchors, but we've also used the platypus anchors, which are very similar. These anchor types are great because they can be inserted by being mounted onto a rig or by hand for smaller applications, and then they're jacked back, which flips the plate which is inserted, and then that starts to utilize the earth capacity of the surrounding soil, as shown on those illustrations. Grouted nails could also be used, but these types of anchors we used on this application for this project because of the simplicity of installation and application. So some great products there. And now on to a meteor case study. This one's going to focus on L walls this time, and it's going to be on the Unite Student Tower on New Wakefield Street in Manchester. Bowman Kirkland were the principal contractor, Curtains were the structural engineers, and we were the temporary works designers. It was a small site with very tricky boundaries. The site had a road and Oxford Road railway station to the north, Vodka Revolution Bar to the east, a river to the south, and then on top of all of that, there was a sloping access road that led to a car park to the west. The design also incorporated a high level and a low level platform just to add to all the complexity and fun. The task was to carry out a reduced level dig to cast a deep piled raft foundation that would support the tall tower. There was an existing basement, but we were going much deeper than that. This image shows the deep basement and the 2 levels. Piled walls were needed to be installed along the lines shown above, and then we needed to create a high-level working platform which would not load the neighbouring structure, whilst also providing some room in the remainder of the site for trades to progress. And then following the piling works, a 2.5 metre deep raft slab would need to be cast against the neighbouring property and the river wall. Both these structures weren't suitable to act as back shutters for the concrete, so this is when cue the L walls to come in from stage right to come and save the day. How do we use the L walls? This image here just shows some common forms of reinforced concrete cantilever walls, and they're made in the form of an inverted T or L usually, with the L being either forward or backward facing. The cantilever wall is a reinforced concrete wall that uses the cantilever's action of the stem, which is the vertical component, to retain the soil mass behind the wall. Stability is achieved from the weight of the soil onto the heel portion or the base slab, and then a shear key can also be introduced to increase sliding resistance. A very simple form of L or inverted T are suitable for low walls, such as less than 6 meters or so. And then anything higher than that, generally there's either a buttress or counterforts are introduced to stiffen the stem and the slab. In the case of New Wakefield Street, we used the L-shaped walls that were precast off the shelf type. And an example of one is shown here. It's ready-made with holes in the base slab, so you can bolt it down to the foundation, which acts as the sliding resistance if required. So let's take a look at the elevation against the neighbouring wall that we provided on New Wakefield Street. The L wall was based on an RC strip foundation that incorporated a shear key into the raft slab blinding, and this provided a greater bearing pressure for the wall and provided stability. That wall was anchored into the base slab with some M24 holding down bolts, and these bolts were placed furthest away from the stem to increase the anchor lever arm and therefore reduce the tension in the anchors. A compressible filler was placed between the L wall foundation and the party wall as well to ensure that no loadings were transferred across. The foundation from the party wall was also checked because of the increase in loading underneath the stem from the overturning force. And the distance between the stem and the wall also had to be controlled to ensure that the stem did not load the wall upon the pouring of the concrete. Space was really tight on this job because we wanted to fill as much as the basement area as we could with the raft slab, so we could encompass as much as the proposed building envelope as possible. And this solution was essentially used along that whole elevation. Another detail that was required to deal with a pinch point, which was along the river wall, between the steps in levels and against the river wall, which was in pretty poor condition, so we didn't want to load that. The geogrid wall enabled the plant and structures to load this area to higher level, but that was also an idea of how to keep the loading away from the wall. And then here you can see the proposed raft slab against the L wall, which is effectively being used as a permanent shutter. And then here's some photos of the area. So we've got the L walls ready for installation along the river wall. The pile rig there is quite busy installing the piles using geogrid reinforced earth batters and walls, which are preventing loading the party wall and minimising the batter extents. So we've got the geogrid wall doing its business on that elevation, and then we've got also the geogrid slope, which is on there to maximise the amount of working space without having a very long batter. The piling works are complete on this photograph, and the reduced level dig can start to begin. The L walls along the river wall are beginning to be installed, and this was by having the geogrid steep slope, this meant that these L walls along the riverside could start to be constructed way before they were finished removing all of the slope works, the high level mat, which links to a combination of different retaining wall solutions to assist the job. Really, it's a kind of working all together. This is a photo from the other side, so looking down onto site, and then the line of the wall, the L walls, run along the river and along the party wall. So that's the approximate top of the L walls, and then the next picture you'll be able to see some of the rebar fixing. On this one now, I'll just hold on this one because you can start to see some of the foundations being put in. Let's just grab my little pointer. So the foundations can be seen along this area, and these went all the way along, and these walls were then bolted into the bottom. And so back onto the other side of the river and looking onto site, we can see the further progress on the steel fixing for the base. And if we zoom in a little bit here, you can see the L walls in place, and you can see the top line of the rebar that shows the approximate line of where the concrete was poured to. So why were L-wall structures the best solution for this project? Well, they were versatile and off-the-shelf items, being able to be adapted to suit different levels, and that was easily achievable with this solution. They were space-saving, so the tight footprint of the site meant that the shape of the L-wall enabled the slab to be cast inside the envelope of the L-wall. Because it was an L, we could still keep the raft slab going right up to the, well, pretty much right up to the perimeter. They were constructed with relatively small plant because we didn't have the benefit of a lot of room on site to have some big boys toys on there. The system also led to cost savings to the principal contractor compared to other solutions that were explored at the concept stage. We explored lots of different solutions being used in different combinations and found that the ones that we went with, the L-walls and a Contig piled wall with a capping beam and the geogrid reinforced structures, offered the best solution, really. So that's been part 2 of the earth retaining structures, which is focused on trench boxes, L-walls and sheet piles. We've also done another one, which is on part 1, which focuses on geogrid reinforced earth retaining solutions. These geogrid reinforced walls and slopes are, in my opinion, the unsung heroes of space-saving solutions on site. They're adaptable, versatile and sustainable. So it's worth checking out that video. Part 1 is on the Andon YouTube channel, which has 30+ videos on various temporary works items, such as demolition, tower cranes, temporary works procedure workshops, and that's just to mention a few. And that really concludes the presentation.